Today, we're going to be looking at how to count efficiently, how to count like a true mathematician. And we're going to start by looking at this problem here. Two restaurants are competing over who has the broadest menu. Restaurant 1, Hilberger's Hotel, against Restaurant 2, Fermat's Pasta Theorem. Now, Hilberger's Hotel has an infinite amount of things to choose from that they could have put on their menu, but they decided for just main course and dessert. Salad, pizza, ice cream, or cake. And Restaurant 2, not to be outdone, decided to do starter, main course, and dessert. Garlic bread, pasta, of course, and then 3 desserts. Now, let's think. Who can offer the largest combination of different meals? Now, you can only take one thing per course. Who can offer the largest combination of different meals? And that is our part 1. So, have a thought. Come up with what your initial assumption might be. Okay, let's look at restaurant number 1, Hilberger's Hotel. Now, out of the infinite options, they went for salad, pizza, ice cream, and cake. And what we can do is we can just write out all the options. In this case, there's not a lot of options to choose from, so it shouldn't take too long. Option 1, salad, ice cream. Option 2, salad, cake. Option 3, pizza, ice cream. Option 4, pizza, cake. That's it. 4 options. That is how many combinations they could serve. Now, you can also imagine visualizing this as sort of a tree diagram where you are advancing along the branches as you make your decisions. So your first decision is the main course decision, salad or pizza. And then once you've made that decision, let's say you're on the salad branch or the pizza branch, you then get to the dessert branch. And once again, there are 2 options here. There is the ice cream, the cake, the ice cream or the cake. And so you can see we've ended up with 4 distinct possible options at the end. And actually, the only thing that really mattered here was how many options we were left with at the end, how many final arrows we had on our tree diagram. So when we're thinking about our options, it is nice to visualize it like this. And so we get those 4 options which we looked at just before. But is there a neater way of working how many options we can make? Because we don't need to know what the options are, we just want to know how many. So what I like to do is something called the slot method. And this is what I would teach to all my students when we're looking at counting problems like this. And all I think is, for each choice we have, I just draw a line, which is a slot. And if you want, you can label it. This is the main course option. And then we also have a dessert option. On the slot, I just write how many possible options were there. So for main course, I could have chosen 2 options. And that is representing the first arrows, how many arrows there were initially. And then how many choices for dessert? Now, there were also 2. So I would write 2 in the second slot. And this is basically saying out of each of the first arrows, how many arrows branch on from that. And then to calculate how many total options or total arrows we have at the end of our tree diagram, we just multiply these together. We have 2 lots of 2. 2 lots of 2 options at the end. So we end up with 4 total options. And using slots, we are always asking ourselves, how many possibilities do I have for that slot? And this, in British schools anyway, is usually called the product rule for counting. Product because we are multiplying these 2 things together. So, can we quickly work out restaurant 2? Well, let's think about what our slots would be. We'd have a slot for starters, we'd have a slot for main course, and we'd have a slot for dessert. So in your head, ask yourself, did you think restaurant 2 or restaurant 1 would have more combinations? Because restaurant 2, there are more things on the menu. But because we can only take 1 thing in the starter, 1 thing in the main course, and 3 options in dessert, when we multiply those together, we just end up with 3 combinations. And actually, we can look at this as a tree diagram, although we wouldn't really do that, and we'll see with the next question why tree diagrams can become very messy. Those are our 3 options. Garlic bread, pasta, ice cream, garlic bread, pasta, cake, garlic bread, pasta, tiramisu. Once again, we just want to know how many. There were only 3 options there. How about restaurant number 3? Furia's Transcorns. Now, a corn-heavy menu, as you can see, although the desserts are a bit more normal. Why would we not want to draw a tree diagram here? Well, you can imagine there's just going to be loads and loads of branches. If I start it off, we've got our corn soup and our garlic cornbread, but then suddenly I'm having to draw 4 arrows at each section to represent each of the mains, and then at the end of each of these arrows, I would have to do another 3. to represent all my possible options. But remember, we're really just trying to count how many arrows do we end up with at the end of this tree diagram. So let's use our slots method. Slot 1 is our starters. We have 2 options, those first 2 arrows. Slot 2, our mains, we have 4 options. And finally, our desserts, we have 3 options. So the total combinations, the total ways you could have advanced along this tree diagram is 2 times 4 times 3, which is 24. There are 24 different combinations at Fourier transforms. So, can we generalize this? And of course we can. And this definition is taken from brilliant.org, my favorite website in the whole world, which I'll talk about actually at the end of the video. And this is that definition for what they call the fundamental principle of counting, or the rule of product. And actually in British schools or in English schools, or at least the schools I've worked in, we tend to call it the product rule for counting. But if a first action can be performed n ways, there's n options in that first slot, second action m ways, the total is nm. N times m, the 2 actions can be performed in that many ways. So for ours, starters, mains and desserts, it's just s times m times d. Thank you, brilliant.org, for that wonderful definition. We will come back to you later. Let's look at some extra examples just to finish us off. So, I have a 4-digit PIN. How many possible options could I have? And I love this question because this is generally how I tend to start this topic with my students. I tend to say, how much time would it take if you were to try and crack this code? How many possible options could I have? And one way of doing this is, of course, using the slots. I have a 4-digit PIN. There are 4 digits, 4 choices I'm needing to make. How many options are there for each one? Well, there are 10 digits I can choose from for the first one, 0 to 9, 10 for the second, 10 for the third, and 10 for the fourth. So when I multiply all these together, you can imagine this massive, massive tree diagram. I get 10 to the 4 options, or 10,000 options, which is a lot of options. And the chance of picking it randomly, you'd imagine, might be 1 out of 10,000. Another way you can think about this is that really we're just thinking, how many numbers are there between 0000 and 9999? Because all the codes have to be one of those numbers. So you can imagine from 1 to 9999, there are 9,999 options, and then there's that bonus option, although no one would choose it, of 0000. So 10,000 options. But what happens if I change it slightly, change that initial condition slightly? I have a 4-digit PIN, but this time it contains no repeated digits. How many possible options could I have? So, let's think about our slots. How many choices, how many possible numbers do I have for the first one? Well, I have all 10 numbers to choose from. So let's imagine I chose the number 8. These are my 4 digits. Let's imagine I chose 8. Well, now for the next one, I can't choose 8. So how many options do I have now? I have 9. And for the next one, 8. Because I've got rid of, let's say if I chose the number 2, I now can't do 8 or 2. And then finally, 7. And so, in this case, I have 10 times 9 times 8 times 7. I have less options than in the one before. That's how many possible options I would have if I had no repeated digits. So we've been looking at what is formally called permutations, which are ordered selections of items. And that word ordered is super important. If you think about the first thing we looked at, which was the menu choices, there was a clear order. We had to have, for example, mains and then dessert. If we had salad and ice cream, you couldn't have had ice cream then salad. That just didn't work. Similarly, for when we had a PIN code, the order matters. A PIN that is 1, 2, 3, 4 is very different to 2, 1, 3, 4. So the order matters. Another classic example of a permutation comes in the lottery. If you get 3, 5, 7, 9, those are very different numbers from 5, 3, 7, 9, or even 3, 7, 5, 9. When we deal with permutations, ordered lists, you get more options than if they were unordered. Keeping that in mind, can we try this last question, which does require a little bit more thinking. I'm dealt a 3-card hand from a regular 52-card pack. How many different hands could I be dealt? So try it, see what you come up with. For example, you might have got these 3 cards. How likely was that to happen? How many different 3-card hands were there? So let's say you, in your brain, are thinking permutations. I know how to do this. I'm going to put some slots down. So in the first slot, there are 52 cards I could have chosen from. In the second slot, there's only 51 because I basically got rid of the 6 of diamonds. Now I've got rid of that and the 3 of clubs, I'm left with 50 cards. And so you can see there's loads and loads of options. 52 times 51 times 50. In fact, let's just do that quickly on a calculator so we can see how many options that is. 132,600 options. So there was a 1 in 132,600 chance of that coming up. But we're thinking about different hands. What would have happened if I got this? So a 3, then a 6, then a 10. Are these the same hands? Well, yes, because in this case, when we're drawing cards like this, order doesn't matter. It's not actually a permutation. Order doesn't matter. So we have clearly overcounted by some amount. But by how much? Well, how many different ways could I have got 6 of diamonds, 3 of clubs, or 10 of hearts? I could have got it like this, which is what I got. I could have got it like this, 6 of diamonds, 10 of hearts, or 3 of clubs. And in fact, there are 6 ways I could have done that. But what are we doing here? We are finding all the different possible selections of 3 cards. We've seen that before. This is actually a permutation within what's called a combination question. Because here, when I'm just thinking about the cards I could have chosen, well, there are 3 ways to choose the first card, 2 ways to choose the next card, and then only 1 way to choose that last card. And so there are 6 total ways of choosing those 3 cards. Now, how is that linked to my original? Well, it's clear I've overcounted. And what I've really done is I've overcounted by a factor of 6. My actual answer should be 52 times 51 times 50, all divided by 3 times 2 times 1. The total possible permutations divided by how many ways of permuting those 3 cards. So here it's clear that we overcounted with our original 52 times 51 times 50, and the amount we overcounted by was a factor of 6, because there were actually 6 different ways of getting that 6, 3, and 10. So the answer is 132600, all divided by 6, which I'm going to do on a calculator, which is 22,100, which is still loads. There are 22,100 different 3-card hands I could have been dealt. If you're interested in formalizing our definition for permutations and looking a bit more at combinations, this new thing we're seeing where we overcount because we need a non-ordered list, make sure to check out brilliant.org. And I'll show you exactly where you should be looking in a second. So just to finish, when did I fall in love with counting? Truly, I fell in love with counting when I discovered brilliant.org. Now, I'm not sponsored by brilliant.org at all, but I just love it. So I've actually popped over to brilliant.org to look at my favourite course, or the course that really changed how I look at counting. It's in the Algebra 1 section of this amazing website, and it's their factorials course. And actually, I've taken a lot of inspiration from this particular section, where they talk about codes and how many possibilities. This is where that amazing definition came from. And we also get this great diagram down here, this tree diagram we were talking about, which shows all these combinations. And really, this course was the first time that there was something at university that I really, really struggled with. It was a combinatorics course, and a website truly, truly made me see it in a different way. This permutations and combinations, these 2 sections here, literally gave me joy in a way that I hadn't got from combinatorics before. So definitely check out brilliant.org. Thank you, Brilliant.org, for everything you have taught me. You're amazing. Okay, back to finish the video. So, there we go. Hopefully you can also start to fall in love with counting a bit more and to just start counting the world around you. Thank you very much for watching.